is an electrophilic aromatic substitution reaction. So you guys are familiar, again, with addition reactions. This top one is an example of an addition reaction. And it's an addition because you basically add something across the double bond. And so the electrophile gets attacked by the double bond, and then the nucleophile ends up attaching. Okay, so that would be an addition reaction. Now, in an electrophilic aromatic substitution reaction, it's actually known as an addition-elimination reaction. We'll show that on the next slide. Because what you essentially do is you start the addition reaction, and then when you open the ring up, you eliminate something, and you end up getting back to the aromatic ring. We'll talk about that today. Oh yeah, it's already on there, huh? Gotta get rid of the animations. Okay. So here's essentially the first step of the mechanism. You have an electrophile and a nucleophile. And again, this is we went over this for the last exam. All right. The electrophile gets attacked by the pi bond of the benzene ring. You end up adding the electrophile on one position, and you get a positive charge over here. At this point, the molecule can actually do two different things. One is the nucleophile could come in right at this point, and that would be the addition reaction. And the other thing is this thing that's the nucleophile could come over here and take the hydrogen. Now, the electrophile could also leave, and you're back where you start from. In fact, there's like a third option. It could go like that. Those are all places where that nucleophile could attack the original molecule. Each one of them gives a different outcome. If it attacks E, then you go back to this point here. Right? If it attacks here, that's when we call it an elimination reaction. Now, we haven't studied elimination reactions, but it's a class of reactions in itself. But it's elimination because you're removing something. Okay? So if you do the elimination reaction portion, it's just going to go like this. Right? And then that's drawn out on the next slide a little more cleanly. The nucleophile comes in. Oops, sorry. Oh, I got to change something real quick. Sorry. It's doing that advance on touching the screen business. Let's see. It was in slideshow, wasn't it? Preventer, where was it? Transitions, there it is. Not. I don't know why I keep saving that. It doesn't remember somehow. Okay. Did it just do that? Weird thing. All right, better. Okay, except for it's not better at this end. Let me try this. Oh, there we go. Okay. Yeah. So you can get an elimination here. This attacks, and then the double bond reforms, and then you get the aromatic ring. And the reason for the formation of the aromatic ring is we talked about resonance energy in aromatic rings before, and how much more stable the aromatic ring is when you have it, and so that's the major driving force for this reaction. Another thing to understand about the mechanism is there are a lot of resonance structures involved in the intermediate. So from this structure, you could move that over here, right, like that, and then this bond can move to here, and then you end up with this. And then if the nucleophile comes in again, it could form the double bond that way. Okay. there's a couple of different ways that double bond can form from either the original structure or through the resonance structures. Sorry. But there are, one of the reasons the intermediate is more stable is because it does have a lot of resonance structures. So, at least in this first part of the chapter, the mechanisms are all entirely the same for this part. That is, when we're doing a substitution reaction, the only thing that's really going to change is the electrophile. So I'm going to show you some different electrophiles. Oh, yeah, so side note, memorize these. Okay. It looks horrible, but it's not so bad. We're going to go through each one of these. The mechanisms for all of these are the same, and what's going to change is the electrophile. So the way you memorize these is on the one side of a flashcard, you're going to put that, and you can put the name. It's called an acylation. And maybe I'll just draw a flashcard for you what the sides would look like. So on one side, you're going to have, let's see, this will be one side of the card. This will be the other side of the card. One side, you'll have benzene. And then the reagents. So you're going to have, for example, R, C double bond, and then it's Cl. That was the reagent that was on the other side. And this is for a acylation reaction. And I'll explain why that's called acylation when we get there, but it's called an acylation reaction. And then the other side, you just draw the product. Like that. Okay. And so you draw the acylation and the reagent. Oh, there's a catalyst for this. It's aluminum chloride, sorry. Like that. And that would be one of the cards. So you know that I drew, going back just a second to this slide, that's actually this one. I abbreviated this. This is actually, if you draw the Lewis structure for it, the Lewis structure for that one is this. I just typed it out because it's easier to write out. But that's the same structure. If you draw it, you'll see that's the same Lewis structure. What? Yeah, right? That's one of those things organic chemists do. We weren't interested in it anymore, so it just floated away. In the mechanism, when I draw it for you, you'll see where it ended up. But on this kind of memorization, I only care about what the starting material is and the major organic product. That chlorine becomes part of an inorganic product, and we just ignore it. So when I actually draw out the mechanism and show you all the steps, you'll see where it goes. But for the most part, organic chemists are notoriously bad. We write equations that can't be balanced like all the time. I know. There's whole papers people have written, I think I mentioned, whole papers people have written about how pedagogically, how teacher-wise, that's a really bad thing, but somehow we keep doing it. And so there are books that are trying to correct that, and like it bugged you, right? When I first did it, it bugged me. Like, where did that go? and organic chemists always say, well, I wasn't interested in it anymore, so I just wanted to see this. I'm like, well, but that doesn't help me. But yeah, we'll try to get through some of that. Anyways, I'm going to go through actually all of these. Oh, animations. So we're going to do the halogenation reaction first. You do not have to know how all of these electrophiles are made, but I want you to know what the electrophiles are, okay? So iron, like in this compound here, right? What's the charge of the iron here? You guys know how, you can't do it from the periodic table because it's one of the transition ones, but you can do it based on the bromine. What's the charge of bromine? -1, and there's 3 of them, so the iron is +3. Okay, so the iron, and this is true for a lot of the electrophiles. In fact, all the really good electrophiles have a big positive charge. So the iron has a really strong positive charge. It's a 3+ charge in the compound. And what that does is this bromine, it gets attached to it. It gets stuck on it. Okay? Because the bromine's got these big electron clouds and it likes to stick to it. And what that actually ends up doing is it creates a strong dipole in the bromine molecule. And the positive side of the bromine is what's going to attack the benzene ring. So this is the electrophile. It's a Br with a strong positive charge on. That's a delta. It means a partial positive charge. So this is my electrophile. Okay, so first step is it generates that electrophile, which is the Br+, basically. Okay. And that's just some stuff that I talked about just now. I just said it instead. Oh yeah, hang on. Did I? Oh, I didn't draw I should have put a blank slide in, so let me draw the rest of the mechanism down here. So I'm going to start with a benzene ring. Draw a benzene ring down here. And then a bromine with a partial positive charge on it, like that. That's my electrophile. And the rest of this over here, on this end that I've drawn, that's all of this other stuff. Okay, but you just have to remember the electrophile is the Br+. So what does the Br+ want to do? Right, that's what's over on that side. Br+ attracts the electrons out of the ring and it breaks one of these pi bonds. And it does that, and then the electrons go over to here. Okay? So what does that leave me with? The bromine will be stuck on the ring. Like this. All the other double bonds will be still there, all right? And then up here I have positive charge. Now, I'm going to draw something in. I'm going to use different colors so you can see it a little easier. So, no, I got to change that. Okay, so on this carbon here, what was there before the bromine was there? A hydrogen. Yeah, we just remember on benzene we don't draw it. So I'm going to actually draw it in now because it helps to understand. I'm put a hydrogen here, and that hydrogen's still here. Okay. Now the way you finish the reaction mechanism is you have to make the aromatic ring again. And to make the aromatic ring, the Br- that you, so when these electrons go this way, right? I'm sorry, wrong thing. When those electrons are going there, you end up with a Br-, and that Br- will come in here, and then this bond will reform the double bond. So the final product when that happens will just be the brominated benzene, so bromobenzene. The other product would be HBr that comes out of this, right? And then because of this, and you have this still, and that's a catalyst. It just is used to help the reaction be faster, but then actually it gets returned back to what it was originally. Okay. This plus HBr is one of those things, again, like in organic chemistry, it's not an organic product, it doesn't have carbon in it. We just suddenly lose all interest in it and don't draw it. Nothing balances. So I'm going to try, if it doesn't balance, I'm going to try to write them as balanced equations because I know how bad it makes you feel. So it made me feel anyways. I don't know about you guys. Okay, we're going to look at nitration. And I actually want you to memorize this. This is the one I want you to memorize, okay? The reason is it's very common to see this kind of mechanism. So this is just going to be, if you're going to go on in organic chemistry or in chemistry in general, this is one of those things you'll have to know. Okay, so I have nitric acid and sulfuric acid, and this reaction that we're talking about is called is a nitration reaction, and that is to take benzene like this and form nitrobenzene like this. Okay. So we're going to look at how the electrophile gets made, and then I'm going to redraw the mechanism for the nitration of benzene, and you'll see how similar it looks to everything else. But in the first step, sulfuric acid is a very strong acid. So nitric acid will actually attack like this. And then this is hydrogen sulfate. This is just HSO4 minus. That's how you normally see it in like a general chemistry class. It's after the sulfuric acid loses one of its hydrogens. And this is the intermediate that's formed in the process of forming the electrophile, okay? So if you look at this, what is that? It's water, right? It's a stable molecule, and that molecule will break apart like this, and it'll form water, and this is known as a nitronium ion. Okay, now its structure is this. And again, it's a very strong electrophile, has a positive charge on it. The nitrogen wants to get rid of the positive charge, so how's it going to do that? It's going to try to grab electrons from something, okay? So this is your electrophile. It all fit in, it all fit in. So I'm going to draw like the nitration of benzene using that as my electrophile, and then you guys will talk me through like the steps, okay? So let me make a little whiteboard. I can make a world map, isn't that cool? Sorry. Too much time on my hands. Let's see. I'll do that. It's easier to draw on. Okay. Weird. Benzene. All right, we're going to do the mechanism. And then the nitronium ion. This was formed previous to the benzene, right? Coming in. So it's this. And there's a positive charge on the nitrogen. So what's going to happen? Right, it's going to open up, the benzene ring is going to get opened up, right? Where are the electrons going to attach? Yeah, because that's where the positive charge is, right? So this bond, and I can use any of these bonds, so I don't want this to be confusing, but I'm going to use one of these instead, because I have this bad habit of always drawing it from the same place, and then people learn that that's the place that attaches, and there's no reason for it other than it could be any of them. So I'm going to try to switch things up occasionally. Now, in order to have the right number of bonds on the nitrogen, right, I can't violate the octet rule, so I got to open it up like that. And what I end up with is this. And then what else do I need? Positive charge on the ring. And then what didn't I have drawn in before? I didn't have the hydrogen drawn in, right? So it's going to sprout a hydrogen. So I'm going to put it in here just to remind you it was there to start with, like that. So you notice the steps are exactly the same. The only thing that's different is whatever the electrophile is.
Why did you lose the double bond of the nitrogen?
Oh, because I could only have 4 bonds on nitrogen. If I would have kept it, it would have been 5, yeah. So the Lewis structure for this is a nitro group. This is the Lewis structure for a nitro group. Can you see that bright green? I can't. One. Be easier to see it right now. Okay, so that's the start of the nitration. What's the next step? What do I have to make? Right. We go back to the aromatic ring. So something has to come and get that hydrogen, and you notice there's nothing on the slide right here that I can do that with. But if you remember, it's the HSO3. Let me draw it in another step. So I'm going to redraw all this. You don't have to redraw all this, but I just want to do it. I have that, and I have the nitro group down here, and then I'm just redrawing it a little more compactly. That, then HSO4 minus. That's from the earlier step where I reacted with the sulfuric acid. And then I end up getting nitrobenzene. And if you want to get lazy, just do that. That's what most people do at that point. Sulfuric acid is a catalyst in this reaction. It is the acid. So again, there are things right over here like H2SO4 that we'll see in each of these reactions. This is the catalyst. I'll put cat next to it. It's not a cat, but you know, it's a catalyst. And I don't know why I drew only in the bottom right-hand side of the slide, but there it is. You could add embellishments on the top if you want. I don't know. I zoomed in and didn't pay attention to where it was. All right, questions? So I'm going to see if you guys can guess what this one is. This is what we're going to do. And this is kind of a wicked reaction to do. It's super dangerous. Well, the nitration's super dangerous too, but we do it all. You know, it's super dangerous. There's, like, as you do more chemistry, you sort of like what was super dangerous like last year was not so super dangerous this year. So we kind of do it all the time, but they're actually fairly dangerous reactions to do if you're not careful. So this is the reaction we're going to do. This is called a sulfonation reaction. So it's H2SO4. And it's what they call it, it's got a name. Called fuming. Now that just sounds bad to start with. You just take sulfuric acid and you boil it. So like concentrated sulfuric acid already is like super dangerous, and then boiling concentrated sulfuric acid fumes, white smoke comes off of it, and that's what they used for this reaction. So it's called fuming sulfuric acid. And then what you end up with is a sulfonic, what's called a sulfonic acid. And let me do it, I'll do it like this, the Lewis structure. So this is benzene sulfonic acid. That's the name of it.
sulfur have 6 bonds?
Oh yeah. So why does sulfur have 6 bonds? That's why I decided to draw it. It's in the 3rd period of the periodic table, and it can violate the octet rule. It will have 6 bonds because it has 6 valence electrons, and it can make 6 bonds. I know. Had you been in my 1A class when I drew it, I would have said, okay, we're just going to pretend this didn't happen. The octet rule is only a mild suggestion because it only applies strictly to the 1st and 2nd periods. And really, only the 2nd period. And really, only carbon, nitrogen, and oxygen, and fluorine. And then beyond that, you could violate the octet rule. So that's like, what, 90% of the periodic table can violate the octet rule? Yeah. I always tell people I lie to them all the time in 1A. And that's one of the lies. We just say, oh, it's the octet rule. And everybody's happy. Then you violate the octet rule, and it becomes the octet suggestion. But yeah, for organic chemistry, just remember the octet rule for the most part, except for like sulfur and phosphorus. Phosphorus will make 5 bonds because it has 5 valence electrons. Okay. Which will be important if you learn about DNA and how and ATP and all those are called phosphodiester bonds. You draw them with 5 bonds all the time. So that's where it's kind of important for most people. Okay, so this is the formation of the electrophile. This is actually on a slide 2, but I thought I'd write it out here. And to do this, you actually have to draw 2 molecules of the sulfuric acid. So I'm going to draw it twice. I'm going to draw it out just to help you remember it, because then you'll draw it out. A lot of times books won't draw that part out. They just don't even want to worry about it. And this is the heating. You're heating it pretty hard. So let me ask a question. What was the first step in the formation of the nitronium ion? When the nitric acid and the sulfuric acid were together, what was the first step? Go back and look. It's the one we just did.
The nitric acid attacked the hydrogen.
Yeah, so we protonated the nitric acid. So this reaction is the same. But this falls in the class of reaction called the self-ionization reaction. Water has this reaction too. That's how we get hydronium and hydroxide. So it's a self-ionization reaction. And you only get significant amounts of it if you heat it. You have to heat it. So you end up with oops, I left my oxygen out. I'll just do that. Spell Haas. You're going to end up with this. Now, what's going to happen there? Right, a positive charge here. What is that again? It's a water molecule. So the water molecule breaks off, and that creates your electrophile. Now, I'll show you when I draw this. You'll see it, hopefully. So sulfur is supposed to have 6 valence electrons, but it doesn't in this case because it just lost one of those electrons to the oxygen when the water click came off. And so the positive charge is here. And that's your electrophile. Now, a lot of times when you see this, part of the fuming sulfuric acid bit is actually the fuming part that people see is this. And this is sulfur trioxide. Has a positive, oh no, no positive charge here. I got rid of the positive. But this is strongly partially positive because of all the oxygens, the electronegative oxygens that are on it. So you'll see interchangeably these two structures in the mechanism for the reaction. Right? Now, what didn't I draw over here? The other sulfuric acid, right? And that's actually this. Is the same as in the nitration reaction. So this will be the base that comes in later. I don't expect you to remember what all the bases are. We're just going to call it B at some point. And we're just going to call this guy the base. And that's what's going to finish, that's my nucleophile later. It's what's going to pick up the hydrogen. Now, so that's the formation of the electrophile. And so what I'm going to do is I'll start the mechanism, and then you guys will see it finishes the same way. Okay. So here's my mechanism. Start with the benzene ring. I don't know why I can't draw straighter lines, but I can't. Benzene ring. And then S, I'm going to redraw this guy. That's my electrophile. And the first thing that happens, right, benzene ring breaks open. It attacks the sulfur because that's where your positive charge is. And then you'll end up with this. That's weird. Mess you up if I do this. It doesn't matter which side of the double bond you go onto. I'm going to draw it at the top. Now where's my positive charge? It's on the other side, right? So that's over here. And again, right, I didn't draw the hydrogens in earlier. There's a hydrogen there. And then my base, which is my hydrogen sulfate, closes the ring up. And then you end up with your product. Like that. Okay? So that part's always the same. It's the electrophile gets attacked by the benzene ring, and then the base comes in and makes it aromatic again. The only thing that's different in all these reactions is how the electrophile gets formed. Right? The ones I want you to memorize, right, are that nitration one, because that's a real important one. You see how it's just like the sulfuric acid one where you protonate and remove a water? And I'm going to show you one other that I want you to know. So again, this is actually drawn out for you on later slides. I just wanted to draw it out. This is the actually the other one that I want you to memorize. So far we have the nitration formation of the electrophile, and then this is the acylation. Okay, now an acyl group is this. Oops. It's this guy. And an acyl group has a carbon double bonded oxygen on it. So that's just known as an acyl group. The formation of the electrophile is again, similar to what we've done before. Let me draw it on a blank slide because, yeah, I want to have a little bit more room. Yeah. Okay, so you guys are comfortable with R. R is anything. Any long carbon chain is R. It could be branched. It could be a cyclohexane. It could be all kinds of stuff. Okay. So here's my acyl. It's called an acyl halide. This is the acyl part, and this is the halide part. Halide for halogen is one of the group 7s, okay? So what happens is the catalyst for this reaction is aluminum chloride. And I'm going to draw this in a way I think it's a little easier to understand how it happens. The book does this thing where they, and it's pretty common, they show all the arrows moving at one time, but they don't have to be drawn that way. Okay, so aluminum, what group is aluminum in? Where is it at?
3.
It's in 3, right? Or 13. But it only has 3 valence electrons, right? So aluminum, this guy here, right, is missing a set of electrons to satisfy its octet. Now, again, it's one of these ones that doesn't have to satisfy the octet. Because it starts with 3 valence electrons, it still wants a pair of electrons, okay? So what's going to happen is the chlorine has electrons on it. Right? It's got an octet of electrons. Let me do like this and maybe you can see it better. These ones are hiding. There. Yeah, that's easier to see. What's going to happen is the chlorine is just going to get stuck on the aluminum. So he is going to find himself stuck over here. So what that does is it does the following. It forms, I'm going to draw it down like this because I drew it too big. It's going to draw it out like this. Like that. And I'm going to have a positive charge here and a negative charge here. And a pair of electrons from the oxygen will do this. It will kick the chlorine off like that. The resulting ions that you get, so you get a pair of ions out of this. One of them is this one. And the other one is AlCl4. And it's got a overall negative charge to it. Okay? That's actually known as a complex ion. It's actually fairly stable because the aluminum wants to pick up that extra set of electrons even though it has a charge on it. This has a fun name. I like this other guy has a fun name. It's called an acylium ion. It sounds like acyl, like A-S-I-L-L, but it's A-C-Y-L-L-I-U-M ion. And that's your electrophile. Okay? So the mechanism for it, again, once you have the electrophile, the mechanism goes like this. You have a benzene ring. You have your electrophile like this. Oh, sorry, positive charges on the oxygen. Now here's something that's hard to get at first, but the oxygen already has like a full set of electrons. If you put another bond on it, right, it'll end up with too many bonds on it. So what ends up happening is the carbon does this, and this gives you a much more stable structure. You'll end up with this. like that, and the positive charge is here now. If you try to go the other way, it's not a very stable structure, so you end up having to back up and redo it. Again, this has resonance in it and all that good stuff. So hydrogen here. And a base can come in and grab that and then reclose it, and then you end up with your acylated benzene. Oh, we should have done that in a different color, but that's okay. I like this color. So you end up with that again. Okay. So that part of the mechanism is, if you know the electrophiles, those I want you to know the electrophiles. The two that I want you to know is the nitration one and the acyliamine one. If you can know those mechanisms, all you have to do is know all the other electrophiles, and you're okay. All right. Questions? A lot of stuff to memorize in this short section. So if you have trouble with it and you need help making flashcards, we could sit like on Tuesday and I can help you with the memorization process and all that. Right, so disubstituted benzenes. Oh yeah, so a dichlorobenzene 1,4, also known as para. We went over this. It's that smell of the men's room. You know, that sort of antiseptic-y bathroom smell. That's what they use for, it's like sterilizing toilets and stuff. It hangs in the toilet. All right. So we have ortho, meta, and para. And I remember we mentioned this last week. Ortho means next to each other. Meta is 1 and 3, and para is 1 and 4. And you can think of it as parallel. They're going in the same direction. Okay. And that's for 2 substituents only. But it's very common to see ortho, meta, and para. So we went over a little bit as well in the nomenclature. I'm not going to spend a lot of time on this week because we sort of mentioned it last week. These have names, and this actually can be called toluene. And then toluene can have a substituent on it, so this would be para-bromotoluene. It could also be called 1-bromo-4-methylbenzene. Okay. So either name is acceptable. You could do it systematically the same way that you've done with cyclohexanes or anything else. Alphabetize the substituents. But because this can also be called toluene, you could call it 4-bromotoluene. The 4 is in relationship to the methyl functional group on the toluene. This one can also be called a couple of different things. Most commonly, when you have an oxygen on it, it's known as the phenol. So it would be ortho-nitrophenol. So this is a nitro group. But systematically, it could also be called 1-hydroxy-2-nitro. Let's see that. Yeah, nitrobenzene. You see all kinds of things when you do the nomenclature. That one's not as common because phenol is a very common name. Okay. So, we're talking about the electrophilic addition to substituted benzenes. The mechanisms are all the same, okay? But the different substituents on the benzene ring have give the rings different properties. So when I say a substituted benzene ring, we're going to take one of the hydrogens off and put a different functional group on it, okay? And those functional groups classify 2 different ways. So just to give you an example, if I have benzene, right? A substituted benzene would be, for example, toluene. And this is replaced in H. So that's what I mean by substituted. Right, originally I had a hydrogen over here. I'll write in purple from here. Now, there's 2 things that these, 2 ways that we classify them. It's either they're activating or deactivating. Activating means more reactive than benzene. And deactivating just means it's less reactive than benzene. So activating's fast, and by more reactive we mean reacts faster than. Okay, because there's two ways to say more reactive. One could be more product. One can just be faster. And we're talking about how fast the reaction goes. So we have substituents. They're either activating or deactivating. And the other type of classification is whether or not they are orthopara, or meta-directing. So if it's a meta-director or orthopara, right? It means this. Here's, if I have a benzene ring like this, and I have a substituent like, let's say that, this nitro groups are meta-directing, okay? That means when you do, let's say, sulfonation, H2SO4, and heat, your product is this. It's sulfonated, and the second substituent ends up meta to the first. Okay? What do you think orthopara means then in relation? It could be either in the ortho position or the para position. So, for example, if I have this, and we'll talk about like which ones are which. I don't expect you to memorize that, like which is orthopara, which is meta, activating, deactivating. I'll give you a list, but I want you to know like why are these activating and why are these deactivating. So we'll go over like the rationale of why, but the memorization of the long list you guys don't have to do in this class. Take the other class, you have to do it. Okay, so if I do this, and I do sulfonation, so H2SO4, I end up actually with two products usually. One is like this. Sorry, I ran out of space. And the other one is like this. So one is in the ortho position. This would be my ortho product. These two are ortho to each other, and that one's my para. How much of each one you get is very hard to predict. Generally speaking, you get a lot of more para than ortho, unless the groups are really small. Then they have less steric interactions, and they end up being right next to each other. Okay? But generally speaking, okay. So, note number one about features, right? Electron donating equals orthopara. So what do we mean by electron donating? Well, in order to be an electron donator, you have to have electrons to donate. So typically, that's a lone pair of electrons. Okay? So I have a lone pair of electrons on this oxygen. Next to the benzene ring, it's conjugated with the benzene ring, so it can donate electrons into the ring. So why is it? Let me see. Yeah, I wanted to put one more note on here. It's also activating. So I have a lone pair. Now, that lone pair can, through resonance structures, donate electron density to the ring. So what that means is the amount of electrons that are available inside the ring is higher than it was without the functional group. Why does that make electrophilic reactions faster? What's that? Yeah, so why does, I'll rephrase the question, why does being able to put electron density into the ring make the electrophilic reactions faster?
Doesn't have to go find a nucleophile.
Doesn't have to go, not that it doesn't have to go find in nucleophiles. Let's leave that to the side. It's kind of related, but not what I'm going for. So, what does the electron donating do to the? Well, so what does an electrophile want in an electrophilic substitution reaction? It wants electrons, right? So by donating electrons into the ring, there's more electrons for the ring to give to the electrophile. And so adding electron density, like through a lone pair, this is one of the most efficient ways to make an active ring, make it more reactive. Now, you guys, all experts in drawing resonance structures now, or actually unwilling experts in drawing resonance structures now, you'll notice that when I push, this is that pattern we talked about, when I push a pair of electrons to the ring, right? Negative charge will end up here, and positive charge here, so that's what this is showing here. The next resonance structure, right? You push electrons, and the electrons go here. Where does the negative charge show up? Right? Every other carbon, right? And in particular, it shows up here, here, and here, right? That means I have partial negative charge here, partial negative charge here, and partial negative charge here. Now, relative to the oxygen, those are ortho and para. So when the electrophile attacks, right, it sees an uneven distribution of electrons on the ring and attaches where there's more electrons. Okay? So when the electrophile comes in, these are where the points where the electrophile would prefer to come in. Now, statistically, there's more positions in the ortho, so if the groups are small, you end up with more ortho. But if the groups are big, because of sterics, it tends to go para. It tends to drop all the way on the other side. Okay, so electron donating, ortho-para directing, and activating. Yeah, those things are all like going together. So electron withdrawing. So nitro groups, right? I'll make a little note here. Nitro group, electron withdrawing. Oops. Meta directing. And they're deactivating. Those are terms that all go together. There's only one instance where they don't. It's pretty a notable exception kind of thing, and I'll show you, where there's a deactivating group that's ortho-para directing. It's kind of schizophrenic functional group. Okay, so there's the nitro group on the benzene ring. That's about it's about the strongest deactivating substituent you can have. It's deactivating because through resonance, okay. So let me draw, I'm going to make a note on here. This is a double bond, right? Double bond next to the ring can pull electron density out. So the things that we typically look at for deactivating substituents are high electronegativity, but in principle, we really are looking at positive charge, and double bonds. That doesn't look like a double bond. Next to the ring. Okay, the positive charge pulls electron density out just because the positive attracts the electrons out of the ring. The oxygen pulls it out through resonance. So there's inductive and resonance effects we talk about here. But here's what happens. All right, the oxygen can pull the electrons out, and when it does that, it pulls this pair of electrons out of the ring, and you end up with a positive charge here. Okay, and then right, you draw the next resonance structure. It's going to look like this. The positive charge will be here, and the next resonance structure, positive charge is here. In general, where you find the positive charge, where is it? Right, you're going to have positive charge here, positive charge here, positive charge here. Now, in an electrophilic reaction, right, what do you want? You want negative charge. So, relatively speaking, there's more negative charge here and here. So if you're an electrophile, you're going to attach, right? There's more electron density in this point. Because what an electron-withdrawing substituent does is it pulls electron density out of the ortho and para positions. And so that's why these become meta-directors. The reactions are slower on the ortho and para positions, much, much slower, but the meta positions aren't as affected, and so when the electrophile comes in, it attaches there. Okay? You like the skinny pen or the fat pen better? What's easier for you to see? Huh?
The skinny one.
The skinny one? Yeah. I like the fat one because it hides my sloppy handwriting. Okay, so we have donating groups and withdrawing groups in general, right? Donating groups put more negative charge in the ortho-para positions. Withdrawing groups put more positive charge in the ortho-para positions. And that's why donating groups tend to be ortho-para directors and withdrawing groups tend to be meta-directors. Just brief summary. You can also see it in the electrostatic potential maps. Like you put an electron donating group on a benzene ring. This is benzene, right? It's bright red in the ring where the electron density is high. And if you put an electron withdrawing group on a benzene ring, you see this bright green, right? And blue because it's pulled the electron density out of the ring. The one, oh yeah. So, this is I'll give you this list like on a test. You don't have to have this memorized. But these are the strongly activating, weakly activating, and then this is weakly deactivating, but this is the ortho-para directors list. So if you have any one of these substituents on the ring, when you put the second functional group, it'll end up in the ortho or the para position. The amount of each that you get, again, like I say, is kind of random. There's a lot of factors involved. Just some examples. CH3, right? Alkyl groups are weakly activating because they have hyperconjugation. We talked about electron donating alkyl groups. Electron donation for alkyl groups is going to affect the substitution reactions. So if I want to predict the product for that, what would you say the products would be? So this is a bromination reaction, all right? You expect products where bromine's here and here. And then also there, but it's the same as the other side, right? So you'll end up with, something happened to my, hang on. It's weird. You'll end up with two products. This will still be aromatic, and you'll have a bromine here for one product, and the other one would be Well, that's an ugly benzene ring, like that. Okay? So ortho and para. I'll skip on that. I think we don't need to go into all that detail. Here's the list of meta directors. So there's strongly deactivating and weakly deactivating functional groups. These are all meta directors. And you'll notice features that many of them have in common. Like I said, to be a deactivating substituent, double bonded next. This is where the benzene ring attaches. Got a double bond next to it. This one has a strongly deactivating. This one has a triple bond, right? And then the sulfonate has double bonds in it as well. I didn't draw the structure out. And nitro groups also have double bonds. The one that's not on here, that should be on here, I'll add it. The really strongly deactivating are these. That would be a strongly deactivating group as well, because it has a positive charge next to the ring, and that withdraws electron density strongly from the ring. And then if I'm doing a meta-directing, I'm going to do bromination, same reaction that I showed before, bromination of a deactivated ring. Right. You get a single product out. Again, this is deactivating because the carbon has the double bond next to the ring. And then a single product like that. And again, that happens because that's where the electron density is highest in the ring when the electrophile attacks. I think that's just about all I really want to cover. Oh, I didn't talk about this. I'll have to cover this next time. But we talked about resonance affecting acid strength, right? Same thing's true with pKa's and aromatic rings. All right, so we'll stop there.